Yes, good morning, ladies and gentlemen. I hope you can hear me now. My name is Dirk Krueger. I'm the spokesperson of the ERCI, European Railway Clusters Initiative. While I'm trying now to share a quick presentation with you, which I hope you can see now. I'm really happy to welcome you for this conference on mobility and COVID-19 and the Science Counterattacks. This is a webinar that we are providing as part of a series of webinars under the brand of the European Railway Clusters Initiative that we have initiated over the time now of the coronavirus outbreak in the world. And I have to say, our weekly series of webinars that we've been hosting since a couple of months now, has been quite successful in enabling new relations between European players in the railway industry. And this is exactly the part and the vision and the mission of our network that we have established 10 years ago with 5 railway clusters from 3 European countries this time. And this has grown to a network of 15 railway clusters that cover now 17 European countries. So almost all important railway industry regions in Europe. We represent more than 2,000 companies, the majority of them small and medium-sized enterprises, but we're also very proud to involve our universities, R&D organizations, education institutions, and other players in the ecosystems that are so important in delivering innovation to the industry. And this is pretty much also the mission today, that we see a new challenge that is also facing the railway transport, being one of the key enablers for reducing greenhouse gas emissions and achieving environmental targets. But now what we see now is that people are reluctant in using mass transportation again, as they fear, of course, infection and spread of the coronavirus. So it is important to understand better the patterns of how the virus is spreading and how the danger and the risk in mass transportation can be minimized. And this is where we want to focus on today, because out of these challenges, new opportunities arise for our members to provide products and innovations to the market that create value to the society as a whole, and in this respect, especially to railway transportation. So ERCI has exactly this mission. Also in times without pandemics, we are at the forefront in matching our partners in R&D projects and in business opportunities through a number of measures, bilateral workshops, task forces. We have very successful task force on cybersecurity and are building up one on mobility and logistics. We also hold innovation awards for a number of years now in order to provide a platform to our members to make their innovation seen in the industry and beyond. So this is in a nutshell what we do today, and I'm very proud that our member Railgrup does host this seminar today. We will, after the summer break, continue our digital formats not in May, as it is said here, but in September, at the date of the initial InnoTrans. So we will start probably on the 16th of September. Please note in your diaries with an introduction on the virtual InnoTrans. Throughout the scheduled date of the InnoTrans is the world's biggest fair for railway transportation. There's going to be a series of webinars, of one-on-one online meetings, also our ERCI Innovation Award series that we are co-hosting together with the Enterprise Europe Network and the Fair of Berlin. So make sure that you don't miss out on the week starting the 21st of September for new virtual opportunities on business exchange, but also, of course, on science and technology transfer. So I will now hand you over for a more detailed introduction of the agenda and the speakers today to Ignasi. Ignasi is the cluster manager of Railgrup, which is also one of the one of the early members of the ERCI, one of the founding partners of the ERCI. So please, Ignasi, take over the stage, and we're very keen on what we're going to see today. Thank you very much, ladies and gentlemen.
Thank you very much, Dirk. Thank you very much, the attendants, the speakers, and also I would like to thank Expochemia, Equiplast, Eurosurface, and Industry Expo, the International Fair of Barcelona, that are hosting the platform and the multiplication of the impacts of today's event. Let me say something about Railgrup. You all know, but yes, we are founder members of ERCI. I'm very proud to cope with the struggling from ERCI to help the industries all along Europe to cooperate in terms of innovation for a better competitiveness of the sector. And this is something very complex and deals with people. So it's something that is also very funny. Railgrup has up to date more than 100 members, covering the full value chain of today competitiveness scenarios, as for instance operators, public operators nationwide as Renfe, private ones as Global Via, local ones as TMB, FGC, Tram, and others. Also manufacturers, Alstom, Siemens, Bombardier, CAF, Stadler, etc., and engineering companies. So covering the whole of the sequence of the value chain related to cope these challenges we have. And one of them, as Dirk very well mentioned, is to address this extremely topic issue of coronavirus, because we need to know and cover a wide variety of approaches. It's not just something that will be coming from one single solution. It's very complex. So this is the purpose of today's event, the Science Counterattack. We need to know first to deal with proper actions, to deal with countermeasures that will help society to recover the confidence with public transport, and also because it's the most sustainable and 20 times more safer than the private car in cities, and also because of sustainability of territories. But it is very sociological issue that we all are quite reluctant to use in a normal mass transit way. The public transport is quite normal. So we need to know, and then if we know, we may deal with proper actions to fix them. The flow of today's event we propose you is, first of all, we need to know about the behavior of the coronavirus. What do we know about them? Afterwards, maybe whenever we are still progressing in having the knowledge about the virus, then we need to at least detect the virus. So what do we know about the detection in indirect detection, that is to say temperature and distancing, or direct detection by means of sensor? And afterwards, dealing with all of that, we need also to know, okay, how is the dynamics of the transference and the movement of the virus, even to know where is the virus moving in the interiors, and then put the proper sensors. And this is the flow of today event. Afterwards, we are going to have minutes for Q&As that are going to be addressed by Professor Joaquim Rigola. So now it's time to introduce the speakers. We are going to start with Dr. Enric Alvarez, researchers of the Research Group of Computational Biology and Complex Systems, BIOCOM-SC, Universitat Politècnica de Catalunya, UPC. Then we are going to follow with engineer Ute Franke from 5 Micron. That is going to deal, she is going to deal with sensor systems to control simultaneously temperature and social distancing in public transportation, transit and waiting zones. That is indirect detection. Then we are going to follow with Professor Carles Alemán from the Barcelona Tech IMEM-BRT Group, Department of Chemical Engineering, Universitat Politècnica de Catalunya, and also together a case use applied to industry by Dr. Pau Tudon, PhD in Chemistry, PhD in Business Administration, Vice President Research and Development of B-Brown Group in Spain, and also the rapid diagnostic nanosensor platforms against these pandemics with Dr. Bergoi Ibarlucea. He's the head of Biosensing Activities in the Institute of Materials Science, Max Bergman Center of Biomaterials, Dresden. And finally, all this detection and behavior of the virus then is going to be accelerated or modified by the movement in the airstream flows in the stations and the public transport vehicles as key elements in the virus spread. So the simulation technologies to be applied to minimize the risk of contagion is something that now needs to be well known. And this is going to be addressed by Professor Joaquim Rigola, Hidden Mass Transfer Technological Center, CTTC, Department of Thermal Machines and Engines, Engineering, Universitat Politècnica de Catalunya, Barcelona. So after that, then of course every one of them is going to reintroduce themselves. So you will have the spelling of the names, and also we will send you the links for the presentations and the recording of the event, and also the possibility to address forward insights to the speakers, apart from address them by the chat at your right, proper questions that are going to be dealt with by the end of the event at the Q&A's session. And that's all, folks, from my side. I hope you enjoy the proposal. Thank you very much. So again,
oh, thank you very much for the nice introduction. So let me start by sharing the screen. I think it's the best thing I can do right now. So I just go here and allow to share the screen. So basically, thanks for the invitation to talk about infections and mobility, and basically at the end of the day, about talking about risk and about how we face risk and how do we interpret risk. So basically, I'm just here talking in the name of a group of researchers in UPC, in Barcelona Tech. We are the group of computational biology and complex systems, and we also share our resources with the Comparative Medicine and Biomedical Center of Catalonia. Basically, we have right now very long list of collaborators, even last year students of undergraduate courses in physics engineering. And first, let me give you the context of what we do so that I can explain later what might be interesting for you. First thing, we as a group had a lot of experience modeling infection diseases, tuberculosis, Chagas, malarias, and other members of the group had the ability to do multi-scale modeling of diseases, subcellular, cellular organs, mainly neuronal analysis and arrhythmias, cardiac arrhythmias. So when the COVID-19 started in China in January, February, we started tracking the data, and when it reached Europe, we already had developed a very simple but very useful an epidemiological model, which is absolutely correct. So thanks to that, we were asked by the European Commission and to Direction General, DG Connect and DG Sound, to provide our input to them. We did the short-term predictions and also general analysis of the development in Europe. We've made right now, I think, more than 100 reports, because at the peak it was just one every day. Now it's one every 2 days, something like that. So we are now collaborating with governments. Any government that comes, we try to support them. We support the regional government, Andorra, the Balearic government, and we're trying to also establish links with the Spanish government, especially regarding tracking outbreaks and mobility data. So that's basically one of the main things that we're doing now, try to know how the virus propagates due to transport networks. But before going into that, let me explain a little bit why we have the ability to make short-term predictions. We basically have been doing 1 week predictions of hospitalizations and intensive care units requirements for Catalonia, and also, of course, we have been to predict the number of deaths next week. So basically, here you can see data from different regions and areas where you can track the total number of cases, the total number of hospitalizations, and EC units used at any given point in time. And then we can predict, because really in the short term, the epidemics is quite predictable at the end of the day. Predictability starts, unpredictability starts appearing roughly after 2-3 weeks, maybe. At 1 month is just basically unpredictable as far as we understand it. But that's not the only thing we did. We also make the estimation of what was the number of real cases, not the data that was people that was going to the hospital, which is a very clear number, but also the numbers of real cases that were behind those hospitalizations, those resources that were used at some point. So if you understand how the intensive care units are used, you can also estimate how the hospitalization really works, and also from biographical study of how the lethality works, what are the real levels of lethality depending on virus penetration in the network of contacts. You can estimate the lethality, and from that you can try to make an estimation of what is the real number of cases. And this is key, because that's a key number that you need to really work out how the networks, the transport networks, are really going to affect from one point to another. I will develop on this point later, but let me show you here first on the left our prediction just 1 week before the study started in Spain, so that we could know with test how many people had gone through the COVID-19. So on the left, you can see our prediction. On the right was the reality that just came 1 week later. We were saying that there were like 2.5 million real cases in Spain. Imperial College was saying something like 7 million. Imperial College was way off. We just were completely right, because of course Imperial College made some clear mistakes that we didn't. So the question is, we do have a very good way to estimate real cases and to estimate the real lethality, and the reason is because we've been working very thoroughly with a good literature review. We have a group with doctors, epidemiologists. We have people working in data, people working in network models, people working in empirical models. We can assess basically all the bibliography before it goes to referees. So we already have a very good view of which papers are really not worthy, which papers are really useful and which papers are normally forgotten by all the community but are really key. And if we don't have the people to do it, we request people in the department to do it for us. So we have now collaborations with people that are, best in the field on everything related with temperature, humidity, and atmospheric science. So one of the first things that came to view very early in April was that the pattern of propagation of the disease was not the typical one of a flu. The typical one of a flu is the one that you can see here in this nice picture, when most of the people here, which are infectious, just infect to maybe 2 people, 3 people, 1 people at the most. Some of them do not infect anyone. That will be a picture of low clusterization or high dispersion, as we call it. The real picture is something more like that. Right now, all the papers have gone through review, so now this picture is basically now confirmed, well, as confirmed as these kind of things can be. We're basically facing a situation where 60% of those that get infected do not infect anybody. So what there are large clusters of propagation. So like, for example, 1 guy here can propagate up to 6, 7 guys. So that's the clear picture that we had already in April. So now the question is how this affects the studies of mobility. So what now is we are focusing on analyzing level 3 data to provide quantitative assessments for the reopening. So there's an ongoing collaboration to know what's the level of mobility, what's the reduction that you need in the mobility in public transport, in visits to different families, so that in case you cannot control these, or in case that you cannot control the epidemics by just tracing and trying to cut the change of contagion, when this is not possible, when the studies of contacts is not possible, how much you have to reduce the mobility. That's one goal we have now with the Spanish government. So in the future, of course, we would like to analyze level 5 data, which is related with small cities or quart or small, 10,000 people, a population of 10,000 people roughly, and how they interact with the surroundings. Of course, it's difficult to go even lower for privacy reasons, and actually we don't think it's actually useful to go lower. So we hope at some point to be able to make this kind of assessment. Actually, we already have some kind of assessments of how it propagates in Spain. We're just talking with the Ministry of Transportation to see how we communicate it, or if we do, or how do we do it. Finally, there's a very important, another important effect of mobility, which is not the effect of how do you need to reduce it, so that when it gets out of control and you don't have any other option but to reduce the contacts, but you need this kind of reduction at this case. But there's another important issue which is related with how dangerous it is for actually a person to take the train, or to take a bus. And here, what we are doing right now, of course, is an analysis of the bibliography. And we must say that we basically agree with the general view that all the groups are having, except for maybe one little feature. Normally, it's very common to put visits to the cinema, taking a plane, taking a train, not on the very high risk, but on the high risk. If we look at the literature, we frankly don't share this view. And let me be more specific. There's been no cluster right now. A cluster meaning a group of contacts that became infected because of one source. There's been no cluster associated with cinemas. There was one supposed cluster associated with a long distance bus that was false. There was some hints that maybe in a plane there had been some kind of a small cluster. It turned out that it was false. long-range train clusters, we have not seen it. So what's the issue there? The issue is basically that we are starting to see that if you really are quiet, if you don't use your voice and you keep your distance, the probability is not as low as being in your house or running free. Of course, we cannot say it's low risk or very low risk, but it's really not high risk. If it will be high risk, we could have seen somewhere a cluster associated. The problem is public transport, because public transport can go from low risk to high risk. It all depends if the people that are in the bus are very few, wearing mask and alone, basically low risk, or you have it crowded, people speaking loudly and don't wearing mask. So when you have the same bus, can be basically any type of risk. That's why it's normally categorized as high risk and not very high risk. But that's the situation. I don't know if technologically can have a solution for that. But that's the way it is. So we've been tracking mobility in Spain and how it reduces. We can do it. We can associate it with bibliography. And now we're trying to develop this early warning system for outbreaks that was used, for example, in China to check how, if you have one area where the incident is very large and you see the fluxes of transport by car, by train, it's not related with car, but with any train, but with any kind of transport, how these connections that people do because they want to move from one place to another, and some areas are more connected in terms of economics or families with others. How do they relate with the spread of COVID-19? And I want to close with this idea: the AVE train, the fast train from Madrid to Ciudad Real, there's been no cluster associated with that. We thought that we think it's very doubtful that anybody gets infected in that train. The relevant was that the train was linking Madrid with Ciudad Real, and Ciudad Real became a very, very bad spot for COVID because it reported a lot of cases from Madrid due to the structure of connections of the people that have the disease in Madrid and how they were connected to the life in Ciudad Real. So I think I will close it here with this key idea. One thing is network problems, and the other thing is whether the transport itself creates a cluster. And here, a public bus is completely different than a long-distance train. So thank you very much.
Well, thank you very much, Enric, for this enlightening presentation, emphasizing let's summarize as the effects of clustering. So it's the first thing to avoid. And also, as we will see, then we need to maybe help, of course, by using personal prevention devices, masks, etc. And also some other issues that are going to be discussed all along the presentation as forcing the ventilation. But we will discuss. Okay, thank you very much. We will have time for discussing a little bit more at the Q&A's step of the event. Let's proceed forward and let's introduce more detailed to Engineer Ute Franke, with almost 20 years of experience in the field of aviation. Had her start at the Brandenburg Airship Developer Cargo Lifter AG, and later on at the aerospace supplier FTI GmbH in Berlin, and with roles such as key account manager of Rolls-Royce and establishment of R&D division with international research projects, were her motivation and basis to found the 5 Micron GmbH in Berlin in 2015. So yeah, 5 years ago. The 5 Micron company story is a young company located in the Innovation and Technology Hub in Berlin, since, as I mentioned, January of 2015. As a stakeholder and managing director are diplomate engineer Ute Franke and Dr. Jan Blondeau. Company was founded with the business idea of development of optical measurement system for highest precise topographic analysis of surfaces and surface closed layers. The company started with 2 contracted projects from Airbus and Rolls-Royce, and 5 Micron's portfolio is based upon photonics technology for high precision measurement systems. Successfully completed technology development projects for the aerospace industry are based on optic methods using light or measurement tasks. The current project are the monitoring and measurement of the wing surfaces of aircraft during flight. Measurement system detects defects and variation in the surface up to 20 microns. And further projects and measurement systems have been miniaturized to fit in an endoscope for engine and maintenance purposes. In this context, a specialized illumination devices as a light communicating system for drones, identification, or other objects have been also developed. This light communication system is operating with modulated flashes, transmitting cover data or any other information. And this is the point, how to deal with indirect detection of the covariance. I presume so, Ute. So I think the floor is yours. Welcome.
Okay, many thanks. Just let me try to share the presentation. I hope you can see the presentation now.
Yep.
Okay, perfect. Ignasi, that was a very comprehensive introduction for 5 Micron. Many thanks. So I think I can skip some slides and speed up a bit because of you have already introduced us so well. So good morning, everybody. Dirk, Ulrich, Krueger, Ignasi, and Enric have mentioned it. So while COVID-19 lockdown rules relax step by step, the employees need the ability to safely return to work and need to travel or use public transportation in the new normality. So we are trying to help to keep the personnel and the passengers safe while traveling. And we have developed a sensor system called Multizen. I'd like to give you a brief introduction into this system. So my name is Ute Franke. I'm one of the 2 founders of the 5 Micron GmbH. We are located in Berlin, Adlershof, since 2015. Yeah, before I give you the information about our sensor system, I'd like to go into a bit of details what Ignasi has just mentioned before. So what we usually do if we are not doing sensor systems for COVID-19. Yeah, we provide measurement solutions for non-standard applications and for rough environment. The industries we are working for is aerospace, gases, railways, or e-mobility. And we are using special methods and algorithms to solve a measurement task. So, for instance, optical methods are very often used for surface monitoring and measuring. I have a simple, a very quick sample of our project we did with Airbus, and Ignasi has just mentioned it. Sometimes we combine it with acoustical sensors and we make sensor fusion. And I give you some words about a Lindy project we did for Lindy last year to measure contents of gas cylinders with acoustical sensors. And I will skip the light because Ignasi has mentioned this already. So we were partnering with the European Commission and Airbus the last years, and we have developed an in-flight measurement system to monitor and measure the wing surface during flight with deflectometry. So deflectometry is a method, and we have placed a set of cameras in a wingtip, in a tip of an aircraft wing. And with this camera set, we were monitoring the wing surface in a very shallow angle. And as we have applied a zebra-like pattern on the other side of the wing, we could see the reflection. And our software algorithms then simply compare the theoretical pattern with the real pattern. We have the images with our cameras. And yeah, so this is so the core competence is not only find the right method, but do the image processing. And we did this successfully for a project for Airbus. And as mentioned before, we use acoustical sensors as well. And we have machine learning algorithms. We are learning what type of signal and acoustical frequency we will acquire, and to calculate then the filling status of a gas cylinder. And we can even identify what kind of gas is in the gas cylinder. So this is what we do usually, yeah. So the changes due to the Corona crisis, we all feel that, and we want with our system support the new normal. So digitization, restructuring, and social distancing. All of these is no longer strange to us. We are very familiar to this. And so we are on the way to the post-Corona era, because we are adapting already current circumstances. So for the mobility industry, this means the new normal is new mobility. And from my point of view, and from the point of having sensors and technology helping the situation, it means that the individuals need to open a bit for defined private data, and let us monitor it in a certain area, and to protect ourselves and our fellow human beings, especially in public areas or while we are traveling. Based on our experience in image processing and sensor fusion, we have started already last year to develop a sensor system to monitor vital values of residents in nursing homes to relieve the nursing personnel. So the principle of our system is a sensor fusion of 3 cameras. We are using a normal RGB camera, it's red, green, blue camera, and combine it with an infrared camera and a 3D camera, sometimes with sound as well. And our image processing algorithms then can identify vital values such as temperature and movement of the people and the persons we are looking at, and we can measure activities during day and night, because we have a thermal camera in there, and we use it for the residents or elderly people in nursing homes. That was the attention when we have started to develop this system. So, but with the new rules, because of COVID-19, we have adapted our system to detect simultaneously the temperature and the social distancing in public transportation. So the architecture of our system.
Sorry, Ute, I think we have a problem with your presentation. Can you please pass any one of your slides, because you are just stuck on the first one?
Oh, really? Is it?
Yeah. So you need. Sorry on that.
Oh, that's
so you
bad.
You are showing the number 8. Then
maybe I can just stay with this mode.
Yeah, maybe. Yeah. Okay. You can scroll by them.
Yeah. Okay. So
right.
This is all fine. I think so. For the architecture, you can see my slide now. Can you see my slide?
Yes, indeed.
Okay, perfect. So for our sensor system, we have a a quite simple architecture. We have a sensor box, including all those 3 cameras or sensors. If we need to attach an acoustical sensor, it's included as well. We have all the processor boards in there. So it's just one box. It's one housing you have to place in your area you want to monitor. And you just need power and a LAN or Wi-Fi infrastructure. And then you can have the analyzed data output on a dashboard or on a mobile or remote dashboard device. So this is all the data will not leave, so the video data will not leave the sensor box itself. So this is the architecture. And usually I wanted to show you a little video, but I will provide after a link to it's a YouTube video. You can check this because we had problems with it. I just made some screenshots. The development the developed system provides a contactless health check with temperature or symptom screening. And on this slide, you see people counting. And we can do it all in real time to monitor people on a platform or on a check-in lane or something like that. And so the security staff will be informed in real time if there is if there are people standing too close together, or if people have over temperature or moving into wrong directions. So on the right-hand side, you see a dashboard, and usually we will only show this dashboard and not the video data. But this is possible if wish, but we have to meet the data protection regulations as well. So as I have mentioned before, the video data is processed while the image acquisition and not saved at any time. So this is why we are safe with data protection rules. So the sensor system enables a continuous automated access verification and provides temperature and counting. And if there are alerts or thresholds you're going to exceed, it's directly going to security staff or to the dashboard of your central station. So as an option, we can, of course, display the video data as well. We have made very good experience with a sort of self-regulation. When people come into a room and see a display with a video, and they have a box around them, and they see a red box because the distance is not enough, or they have temperature, they always think, let's go a bit closer to the sensor and check my temperature. And this is one hand, we can track the data and see the average temperature of groups, for instance. And then we can compare. Last week, all the passengers on platform in the train station 9 had an average temperature of 36.5 degrees Celsius, but this week it's higher. So it's not always necessary to have an individual temperature seen, but you can compare and track over the history. So let me summarize the key features. It's a completely automated system, automated data output on a dashboard, or if you want, you can have the video as well. We have temperature screening, which might be of interest, that it's up to 10 meters, which is better than normal systems on the market. But as we have these 3 cameras simultaneously, and we have different layers and combining it, so we have a quite good distance to screen the temperature. And yeah, the physical distance between people, I have mentioned that already. People counting and the number. We can install it, for instance, in carriages and to get some density information. And if needed, we can give information about the movement patterns of people. It's called activity index as a feature in our system, and therefore we can have an early warning in case of vital values. Let's say the temperature is too high, and yeah, can be the basic of some other actions might be introduced. So I have mentioned the data protection rules because we are in a nursing home. This always, but in public area as well. This is something we take very, very serious. But as we only have raw data captured analytics, we are so far very safe with the data protection rules. Yeah, and day and night operation is no problem. Infrared doesn't need light, so this is all about the features about our camera system. So this is all I wanted to share with you today. If you have any questions, I'm available, and let me know if I can help you with more information.
Okay, thank you very much, Ute. Very interesting. Of course, it's giving us the possibility to at least add some extra points of prevention by taking into account the information coming from the detection of your sensor. So it's quite very much interesting for the operation in railway and in interiors. Yeah, we will have the time to deal with questions. I recall to the audience to address them by the chat at your screen, and then by the end we will try to have a short discussion. So thank you very much. Let me follow the flow and the proposal for Professor Carlos Alemán. Carlos Alemán is full professor of chemical engineering at the UPC, Universitat Politècnica de Catalunya, and a principal investigator of the group Innovation in Materials and Molecular Engineering. He's also associate researcher at IBEC, Institute of Bioengineering Center, and also director of the laboratory of the Center for Environmental Sciences, LCNA of UPC. So I'm recalling to their approach is electrochemical sensors to detect the level of viral load, learning from in silico experiments. So we have the flow of detection as another way of prevention. Carlos, the flow is yours. Thank you.
Thank you very much, Ignasi. So good morning, everybody. Let me first to explain you how we will distribute this lecture. So the idea is that I will share this presentation with Dr. Pau Turón from B. Brown. And this is because we are interested in sharing with you a collaborative project between our institutions, the Polytechnic University of Catalonia and B. Brown Surgical. So this collaborative project is oriented towards the design of a duplex system. We want to detect the virus, and then after the detection, we want to remove it. So I will explain you something about the detection, and then Pau will continue giving flow to the presentation with the elimination and also with some applications that we have in mind for a future. So what I will do is essentially to explain what is an electrochemical sensor. Let me to share the screen. Are you seeing the screen? Okay. I think that you are seeing the screen in a reasonable way. So I will explain you what is an electrochemical sensor to detect the viral load. I will give you only general explanations about what is the meaning of this type of sensors, and of course, I will not give you any detail about what we are doing. And also, I will explain you how in silico experiments can help to the development of electrochemical sensors. In silico experiments are only computational studies. Okay? It's the smart way of call computational studies. And I will explain you about this because our project between UPC and B. Brown has been awarded by an European agency called PRAS with a lot of computational resources to support this project. And these computational resources have been very useful for save a lot of time in the laboratory. This means in the development of the electrochemical sensor. So entering in what is an electrochemical biosensor, this is a very simple device. So an electrochemical sensor is a device that is constituted by several elements. Obviously, we want to detect something. In this case, we want to detect an analyte, this is the general name, that is specifically a virus. In our case, the SARS-CoV-2 virus. In order to achieve this recognition, this detection, we need an electrode, something that is giving an electrochemical response, that is modified at the surface by several reasons that I will explain later, and a bioelement, a biological element. This biological element, what do, is to detect the virus.
Carlos, sorry for a moment. It seems the slide's flashing. So could you please now it's working. Oh no, not now. Maybe can you try to load them again because they are flashing the slides. Now it's okay. Now it's okay.
It's okay? Yes. I think that it's the PowerPoint presentation mode.
All right. Yes.
Problems.
As an IT solution, don't touch anything and then switch off and switch on if it doesn't work. Thanks.
Okay. So we have a biological element that recognizes the virus. Once this recognized event is achieved, there is an electrocommunication. This means that there is a flow of electrons from the biological element to the electrode. And what happens is that you need a mediator. This is the material that modifies the electrode. So at the end, we have biological element for the recognition event, mediator for to facilitate the communication between the biological event and the electrode, and the owned electrode that gives the electrochemical response. Once this is constructed, we have an electrochemical response, like this one that is in the red graphic with two profiles. And this electrochemical response is transformed by electronic engineers into an electronic signal and then into a display. So the typical example of an electrochemical sensor is the glucose sensor used by diabetics in their daily life. What are the advantages of electrochemical sensors with respect to other type of sensors? So they are very cheap. This is important for the community. They have a very fast response, so you have a detection event in less than 1 minute. Chemically, they are relatively simple. They are not very sophisticated from a chemical point of view. And mostly important, they can be so specific as you want. So, for example, in our project with B. Brown, we are interested in a sensor, in a general sensor for coronavirus, not only for the virus responsible of COVID-19, but also thinking in future mutations, we are developing a general sensor for coronavirus. So we can be very specific, less specific, or even no specific at all. How can you construct and things that I am not able to move the presentation? No. How can we construct a sensor? As I said before, we have 3 elements in an electrochemical sensor: the electrode, the biological element, and the mediator, what is facilitating the communication between the biological element and the electrode. So we can combine these elements to develop sensors with more or less specificity. For example, we can use a lot of materials as electrodes. Many of them are commercial indeed. We can use glassy carbon, we can use gold, we can use platinum, we can use even conducting paper, sheet of paper. We can use also different biological elements for the recognition event. We can use antibodies, we can use antigens, we can use DNA or RNA, we can use carbohydrates, since the spike of a virus has the glycoprotein. We can use aptamers, which are very specific compounds, etc. In the same way, we can use a lot of materials to be used as mediators to facilitate the communication between the biological elements and the electrodes. We can use metals, inorganic compounds, polymers, etc. And finally, we have a fourth variable, that is the type of electrochemical signal that we want to register. There are many types of electrochemical signals. We can use amperometry, voltammetry, impedance, or even electric measures. And in this methodologies, what means is that we are detecting a change in the voltage, in the current density, in the impedance, or simply in the electrical conductivity. So playing with all these elements and some others, of course, and combining them, we can design an electrochemical sensor able to measure, for example, the pathogenic load in general. This means bacteria, virus, and many other microorganisms. This is a very unspecific sensor. Or we can design a very specific sensor for SARS-CoV-2 or even for coronavirus, the coronavirus family in general. And to end this part, let's go to see if I am able to move the presentation. Yeah. Okay. let me to show you how in silico experiments, this means computational studies, help in the design of this electrochemical sensor. This is only an example. This is only an example of a molecular simulation, a computational study, in which we analyze the recognition events between the spike of the SARS-CoV-2 virus with an antigen that has been designed by us. So with these computational studies, we are able to extract a map of contacts between the two elements, the spike and the antigen, and then design the chemical modifications to have an improved system. This represents a lot of advantages with respect to classical experiments, because we are saving a lot of human resources, the computer is working for us, and at the end, we are obtaining a lot of results at the microscopic level, which provide us some rationale about this challenging task. So once we have the electrochemical challenge solved, the next part is what to do with the virus that we have detected. And this is the part that Pau will explain you.
Carlos, I'm not sure if it works. Okay, Ignasi, I will try to put it in PPT mode. If it doesn't work, please let me know.
Yes.
Now, can you see my screen now?
No, not yet. Okay, videos in the air?
Yeah, correct.
Videos in the air. Okay, we have seen it. Let me introduce a little bit to you. Because I first introduced Carlos Alemán, but also Dr. Park Turon is a PhD in chemistry, PhD in business administration, and vice president of research and development of the Brown Group. So you are the one to put all that academia into work.
Not really, but I will be part of it. Okay, thank you. Thank you. Then I will go quickly through the rest of the slides that we have prepared together with Carlos, and I thank you to ERCI for the opportunity to share this. And the first question could be why B. Brown is involved with this kind of project together with the university, in this case, UPC. The answer is it's easy. Today, the world has become a little, very big hospital. Everybody is wearing masks. Everybody is trying to follow aseptic protocols. Even we maintain social distancing and try to avoid infection like hospitals as we already know. Then the point is that B. Brown has some knowledge about it, and we would like to transfer our current knowledge to the outbreak that we have in front of us. And the problem, and this from our perspective, is that we have virus in the air. In this article coming from the Procedure National Journal, and then we learned that the virus is carried by droplets, as all we expect, and is spread around in situations where people is crowded as the ones, as you know here. And we need a kind of sensing and later how to eliminate it, as Carlos explained. Can you see the next slide with people in this subway, Ignasi?
Yes.
Yes, okay, then it works. Then the point is where to locate the sensor and how to eliminate them. Our feeling is that the sensors will be placed in several surfaces. On the top where the air is entering into the train, or just in the floor where the exhausted air is coming out. But most probably, people will be wearing sensors in the near future. Because we need to know information about how the sensor is detecting the viral load. And you can imagine that we will hear some sounds coming from the central station saying the viral load in this train is very high or just very low. Please take care, put face your mask or whatever is needed to keep the social distancing. Then This is the first step. Second is how to understand and how is the virus behaving when you try to kill it. And the classical mechanism to kill the virus is using temperature. That's why in our project, together with UPC, we try to learn how the temperature is affecting the virus. We know that temperature is usually giving energy to the molecules, and this means that we are comparing, as you can see in the picture, how the SARS-CoV-2 spicule is behaving in front of the temperature, comparing 25 Celsius degrees with 100 Celsius degrees, with this root mean square deviation of the atomic positions of the whole molecule, the whole number of atoms. That is a really big system. And what we are learning is that some areas are moving specifically related to this temperature stimulus, and then we will try to project this to the sensor or to the methods to kill it. What science can apply to these inactivating systems? Then among a lot of different solutions that we need to be careful, as we will explain later, in this case, we selected the approach that we were following to kill bacteria. In this case, is using gold nanoparticles because they are able to convert light to heat. And when you heat a particle, the temperature is increased, and this can be increased to the level that the bacteria can be inactivated. And we are trying to transfer this knowledge to the virus outbreak. Where is the most logical place to put this kind of filters to these barriers to kill the virus? Just close to the sensor and close to the filters of the droplets that are coming in the air. In this case, I tried to make this picture just to visualize how this should behave. The virus should be attached to the sensor. After the sensor detects that the level goes through the threshold that we consider safe, then the light will be activated in the filter and start killing or inactivating, in this case, the infectious virus. This approach is not only necessary for the mobility sector. As you can see, this kind of coronavirus sensors could be applied in the medical sector. That's why B. Brown is looking into it in the emergency rooms, in the intensive care units, just in the operation theaters. In this case, we are used to use disinfectants or aseptic protocols, as I mentioned before. But here I will share a warning that the main problem, at least from my perspective, is that if we use biocides or disinfectants in an uncontrolled way, we run the risk that we make bacteria more difficult to kill. And just we will be out of the virus, but at the end, we will have more difficult bacteria to kill, and this will mean a really big problem. The same will happen in other areas, because today we are using much more disinfectants than in the past. And the right approach should be how to use smart information coming from these sensors, that in the field of the hospitals, we name it the trend, the roadmap to the Internet of Medical Things. And if we transfer this to the mobility sector, we can imagine that we need sensors or ways to kill the sensor in the filters, in the surface, or in the areas that today we have some risk of transferring the virus. We need to disinfect them following the right approach, knowing that the disinfectant is working well, that it's not mutating the virus, it's not mutating the bacteria, and at the end, we have information that the level of contamination is just in the safe place. And I name it a roadmap towards the Internet of Mobility Things. I know that probably you are working on that kind of information until the outbreak, probably in different approaches, but now we need to combine all our expertise coming from the disinfectants and the aseptic protocols that were developed in the hospitals and working together to fight the virus. And this is my last slide. I would like to thank you again for the opportunity to share this approach, and I will be ready to answer your questions in case it's necessary later. Thank you very much.
Thank you very much. Thank you very much, Paul. I think you are introducing some interesting, again, ideas, and statements that this could be killed, first of all. And secondly, that the warning on mutations, that is also very important and has been quite at least not very well informed, and this is very important. So I emphasize that. So we will have time to discuss on that, and also because of the recent, as you mentioned, paper and warning from scientists of related to transmission by air. It's not just a matter of droplets. It's a matter of nebulizing and aerosols. And I don't want to start a discussion on the size of particle being able to be considered as aerosol of nebulization, whatever it means. It's the risk of transmitting that virus by air is significantly, in statistical terms, high. So this is important. This is very important also, and you mentioned it. So thank you very much again. Now it's time maybe to discuss about using platforms. So the importance of detection and using platforms and in the road, as you mentioned, Internet of Mobility of trains and things. I make a play on words on that. So let's follow by Dr. Bergoi Ibarlucea, with a background in biology. Bergoi devoted his career to the field of biosensors. And he, after specializing in material functionalization during 2-year scholarships from 2007 to 2008 at Tecnalia Foundation in San Sebastián, Donosti, in Spain, Tecnalia member of Railgrup, he moved to the Institute of Microelectronics of Barcelona, IMEM-BRT of Consejo Superior de Investigaciones Científicas in Barcelona, Spain, to obtain his PhD in chemistry and developing biofunctionalized lab-on-a-chip systems with optical and electrochemical detection. Since December 2013, after defending his PhD thesis, he joined the group of Professor Gian Aurelio Cuniverti as a postdoctoral researcher in Dresden Institute, where he worked on level-3 electrical biosensors. And since the end of 2019, he leads the biosensing activities of the group. And now his speech is going to be related to these rapid diagnostic nanosensors platforms against the pandemics. Bergoi, flow is yours, and thank you very much.
So thank you very much for the introduction, and thank you for the invitation to this conference. I hope you can see correctly the slides.
Yeah, it's okay.
Thank you. So I'm working in the chair of material science and nanotechnology together with Professor Cuniverti, where we have a big team working with nanomaterials at all levels, from simulations and modeling to understand the physics and the chemistry, to more applications like fabrication, biological applications, engineering, and so on. More specifically in our group, we are dealing with the biosensing activities, starting from micro nanofabrication of the devices, making the bioprocessing to immobilize the receptors to make them specific toward some biomarkers or antigens for diagnostics, integrating with microfluidics to deliver very small amounts of fluids to the chips. And all these things are based on different substrates, like the traditional rigid platforms based on silicon, or also on flexible supports like plastics to make wearable electronics and lightweight. From the current pandemic situation, we all have learned the needs of the medical diagnostics, which should be rapid, cheap, because nowadays we need millions of tests. They should be simple but highly sensitive, and preferably done by technicians or even by the patients themselves to decrease the workload of the medical centers. So this is called the point-of-care devices. So in this way, we would be moving from a situation like this, where we have a centralized laboratory making analysis, to this one where we have a small chip making quickly a test on site. And from the pandemic's point of view, we need there is an urgent need in the transport and stations to prevent the spread of the disease. And it would be a similar application to having sniffing dogs looking for drugs, or the explosive sensors that we can find normally in airports. And among the biosensors, electrical and electrochemical are probably the ones that offer the simplest approach to make a portable device, and they are also highly sensitive. And more specifically, field effect transistors are those who can sense charged molecules around. These are the ones that we are mainly using in our lab. And so they work something like this, where you have a semiconductor channel connecting a source and a drain. And when you have the molecules around attaching, for example, a virus that is attaching to the semiconductor channel, then you will have a change in the electrical signal. And introducing nanomaterial will enhance the sensitivity, because it's due to the surface to volume ratio, it's easier to affect the complete bulk of the material. Not only that, but they offer also a better mechanical resistance to build flexible and stretchable electronics. As it was mentioned in the previous by the previous presenter, together with the pandemic virus, the next big issue in the world is the appearance of multi-resistant pathogens because of the use of excess of drugs and disinfectants. And the traditional ways to see how the microorganisms react to drugs is with by optical means, using some bulky devices like these ones in the picture. But basically what they measure is the growth of the cells optically. But absence of growth doesn't mean that the cell is dead. So it could happen that the cell cannot grow because of the drug, but it's still alive. And for this, we have an opportunity with field effect transistors. We can make use of the cell, exploit the cell metabolism, and because depending what kind of metabolism they have, they will change the pH, producing protons, producing hydroxide ions, and we will see a signal change with the transistors and distinguish the effects of the drugs. For example, here you have a measurement, an optical measurement. So the cells are growing, and when we inject 3 different drugs, this one, cefotaxime, is easily observed because the cells are completely destroyed. But between ofloxacin and kanamycin, we cannot see any change. And actually, they have very different effects. Kanamycin is bacteriostatic, so cells cannot divide, but they are still alive. But ofloxacin really kills them. So if we try to distinguish them, we see that here, these are already now the measurements with the transistor and a comparison with the pH measurement. And when we inject here the kanamycin, the signal keeps increasing because the cell metabolism is still active. However, with ofloxacin, it's flat. With cefotaxime, like optically, we also can see it easily. So in this case, with the transistor, we can really distinguish the effect of a bacteriostatic and a bactericide. And not only that, if we choose a medium where they have also amino acids instead of carbohydrates or sugars, we will see the change in the metabolism. First, how the signal is going down, and then it's going up, because there is a change in the metabolism when they are first using the sugars and carbohydrates, and then they start using amino acids. So not only for drug screening, but also for analysis of metabolism of the cells, this platform can be useful. But for detection of pathogens, we need to be specific. With this, we are just measuring the pH. And to be specific, we need specific receptors. So in our case, we have used different receptors like antibodies, aptamers, DNA. In this specific case, to detect different pathogens, we were using antibodies. And exploiting the possibilities of the microfabrication, it's possible to make a small chip like this one, which is around 1 or 2 square centimeters. And there are 16 transistors here, 16 sensors. And by modifying each of them differently, one could integrate the antibodies specific for different pathogens. We wanted to distinguish pathogens which in an early stage have more or less similar symptoms like fever, diarrhea, vomits. But in the case, for example, of the Ebola virus, this is really lethal. but others like the enterotoxin or the cholera are not so lethal, so it can be important to distinguish them. And so if we take, for example, a transistor for the enterotoxin, ACB is the enterotoxin. When we apply the enterotoxin, the signal is going down. But for the cholera and the BP40, the BP40 is the protein from the Ebola, it remains stable. With a transistor for the cholera, only the cholera reacts going down in the signal. And with the transistor for the BP40, when we have the BP40 from the Ebola, it's going down. So when we compare these transistors measuring the Ebola and compared to a traditional technique like an ELISA, an immunotechnique, where there is a color change and we measure this color change, with the colorimetric technique, we can measure in the nanomolar regime, and molarity is a unit for chemical concentration. And but with the field of transistors, we can go down to femtomolar concentrations, which is showing that the transistors can be much more sensitive. So these were all based on rigid devices, based on silicon supports. But in a situation where one needs to fabricate many devices and send them to many places, the delivery can be cheaper if you save some weight using, for example, polymer foils, which can be also useful, for example, for wearable electronics if you need to monitor some disease on the skin, for example. And the fabrication in this case was this way. We have the growth of the silicon nanowires on the growth substrate by chemical vapor deposition, and we deposit them in the plastic foil by pressing, like stamping and moving in parallel direction in a way that you end with parallel nanowires. Like in this picture, these are the nanowires, and they are contacting electrodes that are in perpendicular position. So in the end, we have the electrodes connected by these parallel nanowires, and the final construction would be like this. We have this plastic foil with the nanowires connecting these electrodes. We made some bending tests also to confirm that if there is some bending due to band manipulation, or in case of skin electronics because of the bending of the body. And by bending the devices to 8mm radius, after 1,000 cycles, they were still showing good characteristics. In this case, we were measuring with DNA because it's a molecule that is strongly charged, negatively charged. And after a hybridization process, by detecting the complementary sequence, we'll have even more negative charges. So the coronavirus and the H1N1 influenza that was also doing some pandemics a few years ago, they have RNA instead of DNA, but there can be also hybridization processes, or one could simply make a reverse transcription step to get the DNA copy and detect it. But the advantage is that if you know the specific sequence of a coronavirus different to another one, or the H1N1, which is also different to a different influenza, then you can detect specific genomic sequences similarly to a PCR, but without the need of amplification, just directly measuring it. In this case, we were measuring in dry, so normally measurements with biosensors are done in a liquid sample, but limitation of transistors is the measuring distance. And you can get more sensitive if you simply, after binding and after the hybridization of the DNA, you clean the surface and leave it dry. You increase the distance in which you can measure, and then you get a stronger signal. So in our case, we were measuring and we observed a signal increase when the DNA was hybridizing. And a similar device we got with also with plastic foils, but in this case using a two-dimensional material called molybdenum disulfide. The reason is that with this material, by combining flakes and interconnecting them, you can get larger areas which will interact more with the sample. And so there's more chance also to interact with the molecules that you want to detect. And for the deposition, we got this plastic foil with some electrodes. We passivated the electrodes, leaving some corners available for the connection with the material, and then placed a cuvette filled with water. And since we know that molybdenum disulfide is hydrophobic, it can make a compact layer on top of the water. So we only need to evaporate the water, and we will have our film connecting the two electrodes. and then we remove the cuvette, and we have our device ready. In this case, also another advantage of the molybdenum disulfide is that it can make strong covalent bonds, which offer very good stability without modifying it by using thiol-containing molecules. So the sulfur of these molecules will interact with the molybdenum disulfide in the vacancies where the sulfur is missing, and we will make the immobilization of the antibodies afterwards. We also made the usual bending test to confirm that the signal was not changing. And in the end, we performed the measurement of the BP40, the antigen of the Ebola virus. And we could also measure in femtomolar concentrations. And another question that typically comes to us is, what about the reusability of the chips? Because in occasions, these kind of devices are disposable. You measure and then you dispose it. But in principle, it should be possible also to regenerate, following a similar procedure that is used in protein purification. If you immerse the device in an acidic solution, also with glycine to preserve the function of the antibody, then you can regenerate the antibody. So we perform the detection here. So with higher concentration of proteins, we have higher signal. Then we make the regeneration, the signal goes back, and we can make another turn of measurements. So with this, I think I could communicate that these kind of devices can be useful to develop portable devices that can be used, for example, in transport systems, stations, airports, and so on, for a fast analysis, pre-screening, maybe before going to a PCR in a central laboratory. And they are compatible also with microfluidics to deliver several samples, also for parallelization and automation to increase, due to the small size. One could have several chips, one next to each other, and make several measurements at the same time and increase the throughput of the results. And of course, with all the research nowadays, there are all the time new nanomaterials that are appearing, and one can integrate them to improve the performance in any sense. So thank you very much. And if there is any question, then in the question and answer session, I will be happy to answer.
Eskerrik asko. Thank you very much. Bergoi, very interesting. You also putting some other issues to the fore, because if we detect, so your point is making platforms that for multiple detection, of course, because it is something that maybe we need to know. We need to think over to add extra mechanisms of warning people and recover the trustfulness in public transport use. So it's not just a matter of a current situation; it's much more than that. And also another point that maybe I emphasize to the audience is the one that if we detect a positive, then we need a protocol. I'm talking about the stations and operators. To block the transmission. So this is something is also in the limits of the responsibility. I think we as operators, we need to at least to be aware of a proper protocol if we detect a positive in our areas. At least to be sure that we are able to clean them. And from that on, of course, to put the question as a coordinated protocol with the authorities to prevent communitarian transmission, enlarging the clustering as we have just seeing all the events. So very interesting, very interesting. Thank you very much again, eskerrik asko.
Thank you.
and then. We are moving for the last of today. We are a little late, but still on time. Let's pass the floor to Professor Joaquim Rigola. Kim is professor at the UPC and promoter of the CTTC UPC, Universitat Politècnica de Catalunya. He works in the numerical simulation and experimental validation of heat and mass transfer phenomena applied to HVAC and R systems, participating in the Euro Mobility KIC, platform, Edge 2020 Clean Sky projects from medicine inhalation to aircraft particle protection systems. So I think now, Kim, you have bon dia, benvingut, good morning, welcome. Now you have a hot potato in your hand because of today's let's say publication, confirmation of the positive transmission by air, and it was something that we along our previous seminars and also in participation in the groups with operators in the room, it was something that was at least mentioned. It was not proven, but I will always remember you said we may not discard that this is something that will happen, because we need to know about the mechanisms of transmission, and air is something that could also have some kind of positive mechanism of transmission. You mentioned literally that, and today is proven. Yeah. So hot potato in your hands, Kim. The floor is yours.
Thank you, Ignasi. I have to share it. Sorry. Yes. Okay, can you see my screen?
Not yet.
Oh. Sorry then. I have to. Okay.
Now it's okay.
Perfect.
If you can open now, okay, great.
Perfect. So thank you very much, Ignasi, for the presentation. As I say, Ignasi, I'm Joaquim Rigola, professor at the UPC. Let me briefly start with these 4 points. I'm going to speak a very brief presentation about the Heat and Mass Transfer Technological Center and which are the research topics that are linked with the problem that we have now over the table regarding the COVID-19. And I'm going to split this presentation in 3 main aspects: the flow physics on COVID-19, the air influence on this COVID-19 in airborne transmission, as I say, Ignasi, now, especially in the numerical studies of social distance effectiveness. And finally, I have catch some interesting international journal papers for the numerical simulation of the air distribution in indoor environments. You will see that all my presentation are related with published papers. The 2 first in 2 months ago is not from my group, so I'm working on that, but I'm not presented yet anything. So that's why I use information reference in another international journal papers, but I think are very important to see exactly what we are at this point. Well, in that sense, we are at the research center at UPC, about 40 persons, 15 PhD students, but our main work is related with these 2 topics: the mathematical formulation, the numerical resolution, and the experimental validation of heat and mass transfer phenomena, something that you can see here, a high-performance cluster of 2,000 CPUs. So what we do is develop computational fluid dynamics, computational structure dynamics, interaction fluid structure, condensation, evaporation phenomena, particle insight, and so on. We develop our own codes, we use open source code, and we make simulations of all this process. Here you have another important aspect, which is the thermal and fluid dynamic optimization of thermal systems and equipments. And some typical example is this office. This is our office at the UPC in the Mechanical and Aeronautical School in Terrassa. This is a garden. This is a microclimate. We control temperature, humidity, the prevention of the radiation of the sun, the different curtains, ventilation, and so on. So something directly, specifically related with this problem. This is for obviously energy efficiency, active control system of the air, temperature, and humidity, but now obviously can be applied to the problem of the physical fluid in COVID-19. I'm sorry because today's presentation, I cannot show the videos because I use a different laptop, but you can see that some main aspects that we work is in the natural convection of heat in cavities, internal cavity, which is the velocity profile of the movement, the temperature analysis, and so on. We also work in the development of the shape of droplets and bubbles interface with air or other type of fluids or liquids, and which is the interaction between them. We also work in jets. I'm so sorry because here I'm not available, but you can see, imagine a jet. The jet is broken in some length, and then it's produced different big bubbles, small droplets, or different lines. So how is structured similar to what happens in COVID-19 in in the expelling of COVID-19, or some other projects related is, for example, the analysis of inhale in a trachea, okay, and see the number of particles that go inside. The objective of that is where the particles arrive to the end of our trachea. Other are, for example, the air distribution in household refrigerator, or now we are working in this Horizon 2020 project with the developer of a particle separator for the new HVAC in the new more electrical aircraft. Of course, it's not only CFV, we need also active control systems. So development, for example, here is the HVAC of an aircraft. This was from another European project in Clean Sky Framework. And here is the analysis of the whole HVAC, the control, the regulation of the temperature and humidity, CO2, biopollutants, and whatever. So you can see the framework in which topic our group are working, and then we move to the main point of today. The first aspect is to analyze the flow physics on COVID-19. And the main question is what we know and what we should learn to be better prepared in the face of next outbreak of COVID-19, that it seems it's very possible, or similar disease. In that sense, all the information that I have here is referenced on this paper is from the Johns Hopkins University. I guess that everybody knows that it's a reference on healthy problems and also in COVID-19, and it's published 1 month ago, a couple of months ago, okay? The three main aspects are the generation and the aerosolization of virulent respiratory droplets. The aerosolization now, it's a key problem. The airborne dispersion and the deposition of surface. So the direct contact face-to-face, to touch a surface, or the inhalation of these aerosols by an inspected recipient. This is the problem of the probably aerosolization in the air. In that sense, which are the main preventions? Of course, the use of masks, not only in indoor environments, the hand washes to prevent, of course, the contact with touching previous surfaces, the social distance, something that nowadays is also under questions, is 2 meters, the optimum length of that. And of course, in the under environments, the problem of the ventilation and renovation of the air. In that sense, I think it's very important from an academical point of view to be clear that the transmission of these respiratory infections via virus-laden fluid particles and the flow physics is the basic issue to understand the process. And then if we have understand the process and we control, by all my colleagues that I explained before, how we can measure different parameters that affect it, we can mitigate these effects. In that sense, the main aspects are the droplets, the large droplets expelled with a sufficient momentum to impact directly a healthy recipient by mouth, by nose, by conjunctiva, so by the eyes. The contact, so the physical contact where the droplets are deposited in a surface, and the subsequent transfer to the recipients. And the third point, that nowadays is an important aspect because, as you know, the Global Health Organization has said that it could be possible, which is the airborne transmission. So the inhalation by the recipient of aerosolized droplets, nuclei, coming from the expiratory ejection. So how it can keep in the ambient several hours. Of course, in a very small droplets, but keep there. In that sense, sneeze can generate about 10,000 droplets flowing at about 20 meters per second. Cough can generate between 100 and 1,000 droplets at 10 meters per second. Breathing generates much lower rates of droplets, but much more expired aerosols. So the problem is not only when people is cough, it's only in the breathing. Talking can generate about 50 particles per second at 5 meters per second. Okay, and droplet size are about 0.1 and 1,000 microns. And the important point is that it's almost general known. The critical size range is about 100 microns. So what 100 microns? It's true that there is a range between 50 and 150, depending on temperature and relative humidity. But 100 microns can be the critical range between small droplets and big droplets. Okay, in that sense, the small droplets, so droplets with a range lower than 100 microns, can expel it during breathing, coughing, and so on, and may travel between 3 and 6 feet. This is the general idea of 1 to 2 meters, but large droplets expelled from a sneeze can travel about 6 meters. This is coming from this reference of Johns Hopkins University. So it is true that in general, 1 to 2 meters is the first social distance, but we have to know if exactly, let's say, that the optimum in that sense. Additional problems, as explained before, appears in the airborne transmissions associated with these small droplets suspended and transported in air currents. Most of these droplets evaporate within a few seconds, but form this droplet nucleus, as small as the initial droplets, and can keep in the atmosphere. That's why relative humidity can give a positive place in order to avoid this evaporation. The droplets keeps in a bigger size and then can go down. Okay, but in regions with small relative humidity, the evaporation process produces this reduction of the droplet, keeps in form of duplet nuclei, and can keep in the ambient. This nuclei consists of baryons and solid and residue. These are droplets that are approximately of 10 micron size and may remain suspended in the air for 4 hours. Okay, this paper does not give any data about the number of hours, but it's about several hours. Then, in conclusion, this analysis of physics, the importance of ventilation and the airflow control, which is something that is well known, is studied, especially on energy efficiency reduction, can now be very important, not only for energy efficiency and homogenization of the temperature, but also in the, let's say, the complexity of the dynamic of recirculation effects. And then, from our point of view, better predictions are needed. Then, if we move to our influence on the COVID-19 airborne transmission, I say we have to distinguish the virus diameter ranges from 50 to 2,000 nanometers, and the droplet size, where the virus is transported, with range between 0.1 and 1,000 microns. Then again, the three main questions is the social distance about 2 meters, actually proposed by the World Health Organization and also for the Center for Disease Control and Prevention, is enough. Which influence can have the temperature and humidity, and relative humidity in this aspect, and which can be the velocity effect or the forced convection influence on this virus transport. In that sense, all the information collected in this presentation is also referenced in another paper from the International Journal of Aerosol Science. I think it's from May of this year, so of course very recent, and also take into account to do some academic analysis by means of numerical simulation of this effect. In that sense, this paper, what it does is to propose a couple of persons that affected by the virus and a healthy person, okay, analyzing the simulation for distances between 2 and 3 meters, okay. It's very important to say that in this first analysis, neither the person with the virus and the person with healthy has not mask, so it's without mask, but it's interesting to see how is the evolution of these droplets under three main conditions: light air, so very small velocity of the air; a gentle breeze, which is a highest velocity; and moderate breeze. Okay, the first aspect that you see is how one person breathing or touching has a recirculating of the air in this part, so there is all recirculating after this effect, and also which is an important current of air that diagonally move to the healthy person and to the head. Some analysis of different wind velocities between 0 and 5 meters per second, and also analysis of relative humidity, analyze the fraction of deposition, so like a ballistic effect of the droplets that touch the floor on the ground. So here is B, okay, which is a reduction depending on the highest velocity, but this is the depositive fraction touching, affecting to the coughing human on the left and the healthy human on the right. So here you can see the level of quantity of deposition, okay, that can affect directly to the head of the healthy human without mask, and that's true that without mask. This is going to the ground, so due to the ballistic effect for large size, and this is the suspension droplets. And this is the key point. This is the number of droplets that can be moving through the air. This is a static analysis. These are 2 persons completely white, okay? But imagine that you are moving. Imagine that you are close to this person, and these particles, or these droplets, sorry, can keep in the air, okay? It is true that if we enlarge the distance from 2 to 3 meters, there is an important reduction. It's about 2-3%. There is a going down the position, but it is still some possibility that directly the human who coach can be affected to the healthy human on the right side. This same paper analyzed the influence of the mask. In this case, the mask is the N19, which is about 88% of porosity, so it's a very high resistance. This numerical simulation is working in the worst conditions. So here you have an unrealistic case of a mask separating a couple of centimeters, so there is a part. But the important aspect of the study is that in comparison with the case without mask, the number of droplets are clearly reduced. There is an important delay on the exit of the mouth zone is also observed, and there is a clearly reduction on the risk. So that's important, and we think that now, for example, in some region of Spain is mandatory. The mask is has not only to be mandatory in indoor spaces, it's also, for example, in public space or something like this, in order to drastically reduce this phenomenon. And if we can accept or contrast that at the end, this aerosolization process can be important, the necessity of the mask is clearly mandatory in this case, okay? Among all these points, it is true that although these small droplets can follow the air and can arrive to the healthy human, so there is a small percentage of possibility, but also are available here. Then the conclusion of the second paper is that the COVID-19 who coats can produce these virus-laden droplets in microenzymes and can remain available in the air, exposing the healthy people. The wind effect is presented and can affect the people who coat, but also the people can be have been affected by this COVID. Then maybe additional, let's say, social distance can be affected. This is without mask, without mask. And then it's true that for higher human relative humidity, the higher deposition factors appears, but with this lower human relative humidity, it forces to this evaporator, then the water is reduction, but it remains this nuclei of the virus in the air, so the aerosolization process, okay? It is true that, or the conclusion is that the use of the facial mask is the prevention that completely reduce drastically all these problems. So that's why we think that it's not only for indoor environments, but also for external environments. And finally, to close my presentation, we move to another paper. This is an international journal paper on dengue simulation, but I selected this paper because it's in 2014. So this analysis of energy efficiency and also air distribution in different geometries of trains. In this case, when one patient, when one person infected by some virus expel or catch within the train without mask, because this one in 2014, can see which is the distribution of these particles, of these droplets within the train. Okay, so I think it's important in this case because it's far from the actual situation. So when the people did this simulation, was not thinking on the problem on the contamination by the virus. It's just to see which is the effect of the distribution of the air. Okay, in this case, the publishers present three different geometries. One is clear with the inlet supplied by the external, so by the top part, and exhaust in the down part. Here, the inlet and the exhaust are on the top part. And this is the other one with the inlet of the air supply is in the top part, but the outlet, the exhaust, is in the door. Okay, so it's move the air in the corridor. In that sense, you can see the air distributions. Of course, in the first case, there is a clear distribution of the air coming from the top to the bottom, because here is inlet and exhaust. Here is a recirculation in this part, due to all of them is inlet and outlet from the top part. And here is quite strange because here is to the corridor, so there's also removing part of here. Okay, it seems that the second case was very well compared in comparison with the other two, but it's not exactly true because here the range of the velocity are relatively high in comparison with them. So we can conclude that this simulation, when has been compared with some proofs on the temperature at different points of the train, can be reasonable. In that sense, here you see the evolution of the coach. Here we have the person who has the code, and here you see the distribution of the particles. Remember that in this case, the exhaust is from the bottom, so the particles are moving from the top to the bottom. You can see here, but it appears a clear, let's say, area of suspended particles in the train and also in the part of the corridor. Okay, so it's affected by the previous and the afterward rows. In the second case, it's more concentrated in the top, because remember the second case, the inlet and the outlet are in the upper part. Okay, so all the air is suspended here. And in the third case, it's moving to the corridor. So it goes fast to the corridor. In terms of efficiency, and that's the conclusions of the paper, the air temperature and the air velocity distribution are most homogeneous among the three cabins. But the third case, okay, the main age of air has the shortest among these three cabins. The air distribution system in the third case is the most efficient among the three cabins, and the ventilation efficiency, it means the time that the ventilation is completely removing for the whole train is the maximum ones. So the better efficient in the third case. Okay, it implies that the air distribution system in this third case can be the best one or the most effective to avoid the contact of the droplets removing for a coach problem. Okay. Instead of that, I think it's important to highlight that in this case, a part of the air keeps in the top part, and here maybe is affected by some of the lines. That's why my conclusion is that now the numerical studies has not to only be done in terms of energy efficiency and also, of course, in ventilation efficiency, but also to see where the particles are distributed. Because it could be a case with a high efficiency ventilation, so big capacity to remove the air, but the air can be concentrated not in the corridor, maybe in zones where are the shares of the persons. So in my final conclusions is that it could be interesting to carry out more simulation studies of the physical of the fluid in terms of this air distribution inside public transport facilities or whatever, or indoor environments in general, to generate these results to allow to quantify the risk of contagion, verify and validate these predictions, and probably propose new designs. I meant not only to, of course, increase the energy efficiency, reduce energy consumption, assure the homogenization of the air, but also to reduce these potential outbreaks of COVID-19 in these indoor environments. And thank you very much. That's all from my side. If there is any question, so you have here my information.
Thank you very much, Kim, Professor. I think we have 3-5 minutes maximum for questions. You can put the questions on the chat that you write. You have a specific questions file to put it, or if not, you may use the chat, the general chat, and then we will see it. I would like to start, maybe as a general question for all the speakers. Well, it seems that, of course, we do need more research on that issue. It's not so easy because it's a combination of multiple impacts. So maybe up to now, because we need to keep our lives living. Maybe from an railway operation point of view, we need to think over having a combination of different measures. First, it seems that prevention, the using of the mask, and avoiding clustering as much as we can. So we must design for avoiding clustering and making mask compulsory, absolutely compulsory. And also it seems that forced flushing, let me call it so, forced flushing of air, of course taking into account the point you make, Kim, about, well, we need to know specifically the dynamics in the interior, but maybe in a interior of a unit is easier than in stations, for instance. But in any case, maybe a forced flushing of air could be of help. And also the detection of the actual level of presence, direct and indirect. Finally, if we are able to implement in the whatever filters systems of let's call it killing the thing, then this could be the perfect solution. So what do you mean about that proposal? And also another question, what about the cost of these sensors? Are they affordable for massive use in railway operation or not? These are my first two opening questions.
I can answer you about the second one very rapidly. Electrochemical sensors are in general very cheap. Electrochemical biosensors, which incorporate biological elements, are more expensive, but are not excessively expensive, since we should think that this sensor has so it's not an infinite time of life, but they have a quite reasonable time of life. So I think that they are quite affordable from an economic point of view.
I have seen the electrochemical sensor and the adoption electrochemical field effect transistor are not as cheap as electrochemical, but when they are done in using cheaper materials than the traditional transistors, they can also be cheaper. But we have seen also during the previous months how despite this price, the performance of the commercial ones that have been used were not so successful. There have been many complaints about the performance. I remember in the news, many of the millions of chips that were returned because of bad performance. And this is a kind of a traditional problem also in the biosensors field, that when we try to move from laboratory measurements to the real scenario, sometimes we find problems because of the complexity of real samples. And something that we usually skip in research is to put more focus in preventing non-specific binding. I mean, you will find a lot of research on new receptors, new devices, new measurement techniques, but not much on improving the blocking steps to prevent non-specific binding, for example, or false negatives and so on.
So first, I would like to say regarding the clusters that there are in the pipeline a lot of work regarding quantification of mask, which is reduction of risk with mask, which is a rather difficult topic, but we know they are on the pipeline. So it's going to be more and more common to observe news saying, if you have mask, you could have attended, a train attendant or someone dealing with people. There are a lot of now papers saying, look, if you wear a mask and you have COVID-19, you can be heavily infected, share and interact with a lot of people in the shop or in the bar or in the haircut and not infect anybody. So they are in the pipeline. There's been one last week, I think. And that's going to be basically the deal. The idea it's going to be that if you behave like in a cinema, there's not going to be any problem. So in the short term, detection is fine, but it's more important to make people feel secure that everybody around you is going to wear a mask. It's going to be a much better investment to know the people that take trains, to know that it's going to be absolutely compulsory, And I know that if you can convince doctors that, you know, when you wear a mask is not intermediate risk, but low risk, which is going to be tough, that's how you can regain trust of the people in the short term. In buses, I'm with all the people. I think you will need this extra detection, this extra sensor, or something else, because a bus, you know, someone pops in, no mask, wearing a party. It's like having a party basically in the beach. Bilasar, last day, 35% chance of infection. With this news, you're not going to convince anybody that you're going to get in a bus and it's going to be coming in a party and you're going to have a 30% chance of getting infected. If the trip is roughly, I don't know, 2 hours. If it's less, of course, it would be like 5%, 2%. So that's the challenge the public transport faces, not the train. I think the train has a nice way out, and I think it's just to show these news reports, explain mask, explain ventilation, explain a lot of ventilation, and make everybody comfortable that no crazy guy is going to come in. And it's going to make it like a party. Even if it has the ventilation of a beach, chances are, you know, 20%. While, you know, in the cinema, it's basically 0. So that's my point of view. And now we have a question that I'm not going to answer. Somebody has considered Raman spectroscopy to detect SARS-CoV-2. Anybody? Give it a go.
Well, I haven't seen it for the COVID, but I have seen it for other viruses, which means that for the COVID it could be also used. For the COVID, I have seen other alternative optical methods, which are not Raman, but for example, the surface plasmon resonance. Maybe somebody else here has seen something using Raman for the COVID, but I have seen it only for other viruses, but it should be possible too.
No more questions?
Now, so we are, all of us. There is no more question, right?
No.
I don't know if there is any other part in chat.
If I'm back, that is going to be no more questions. Maybe it's as a summary, it's quite a scientific fact. As I used to mention, science does not only begins with a question, it also ends with many more. And this is science. I mean, it's something that the certainty is not a real fact, because we need to deal with uncertainty. So I think has been very clear. Of course, we have a big issue in our hands, but I can summarize that maybe the flow that we have just and you have been very brave in presentation the way you did. Is the way to do it. I mean, it's not just a matter of a single magical solution. It's quite related to a combination, as you emphasized it. Also, prevent and also add detection of, as you mentioned, Enric, crazy guys, crazy people. The ones you mentioned, I think, in Premià or Vilassar. So this effect should be prevented because it's the number one. Also, the using of flushing, the using of extra ventilation, and progressing in the using of detectors and, let me say it, killers. And this is the point. So no more than that, and nothing else than that. Okay, I would like to thank all the attendants. Thanks all of the speakers. Of course, we are going to be in contact with you and receive your insights. We will receive requests for sending the presentation. So please addressed to us if you need the presentation. I repeat, so please address to us by means of a mail, for instance, to Elena or myself or Railgrup, and we will manage to send you the presentations. And of course, any other insight that you will have to forward to the speakers or to ourselves to coordinate, please do it. Now you have in your screen the mail of Elena Dimitrova, our manager in charge of that. So please, the ones interested in receiving the presentations, please send an email to Elena. Thank you, Spokimia, Eurosurface, and Expos about the organization and hosting the platform. Also, thanking ERCI and encouraging the rest of people and clusters to join efforts and be resilient to cope with the situation. So nothing else. Thank you very much, and we hope you enjoy the presentation and have something for being a little bit more resilient on that. As we used to say, huge animos, and thank you very much. Bye.